All right, today we're going to talk about 3-5 rational functions and their graphs. So we're going to kind of expand on what we talked about last class with simplifying rational expressions and finding the restrictions of a rational. So we're going to build on that. First thing we're going to look at is the domain of a rational function, which is going to expand on our exclusions. So remember that we cannot divide by 0. So we want to look at the denominator and figure out what x cannot equal. So looking at a, f of x equals x squared minus 9 over x minus 3. We know from this denominator that x cannot equal 3. So the way we write our domain is going to be from negative infinity to 3 union 3 to infinity. So this is a interval notation method of showing the domain of all real numbers, negative infinity to infinity, excluding 3. So if we look at b, f of x equals x over x squared minus 9. We want to start by factoring. So we have x over, so x squared minus 9 can factor to be x plus 3 and x minus 3. So from this denominator, we know that x cannot equal negative 3 and positive 3. So our domain is going to start from negative infinity to our smallest exclusion of negative 3, union negative 3 to positive 3, union 3 to infinity. And c, f of x equals x plus 3 divided by x squared plus 9. X squared plus 9 can't factor, but if we were to set it equal to 0, or not equal to 0, I should say, we have x squared cannot equal negative 9. And if we square root both sides, we have x cannot equal plus or minus 3i. But because we have an I here, this is not real, and we're only looking at our real numbers, so there are no restrictions. And because there are no restrictions, that means our domain is negative infinity to positive infinity. All right, so because we're kind of short for time, we're going to skip this next section. So now we're going to look at all of the subcomponents of the rational function graphs. The first thing we're going to look at are vertical asymptotes. Vertical asymptote are our dashed vertical lines that we use to express when our domain does not exist, or one of the ways we express it. So your book's theorem says that if the function f of x is a rational function in which p of x and q of x have no common factors, which means that we are simplified, and a is a 0 of q of x, the denominator, then x equals a, is a vertical asymptote of the graph of f. So if we look at a, f of x equals x over x squared minus 9. So if we factor this, we then have x over x plus 3, x minus 3. We know our domain x cannot equal negative 3 and 3. And because our fraction is simplified, those domain values are actually our vertical asymptotes. I abbreviate that VA. And when you write these, you want to write them as equations. So x equals negative 3 and x equals 3. Okay, if we look at b, f of x equals x plus 3 over x squared plus 9. We talked previously that there are no restrictions. So this would be an example when we have no vertical asymptotes. Okay. And C, f of x equals x plus 3 over x squared minus 9. If we factor that, we have x plus 3 divided by x plus 3 times x minus 3. So notice if we simplify, we can cancel out our x plus 3's. Remember, we said that if everything cancels in the numerator, we're still left with 1 over x minus 3. So now our vertical asymptote is going to be based off this denominator. So our vertical asymptote is going to be x equals 3. Now, one of the things we can talk about, if we look back here at the beginning, based off our restrictions before we cancel, we know that x cannot equal -3 or +3 from our domain. So then the question is, what is happening at x equals -3 if not a vertical asymptote? Okay. And we're going to answer that question in this next section. So a value where the denominator of a rational function is a 0 does not necessarily result in a vertical asymptote. There is a hole corresponding to x equals a and not a vertical asymptote in the graph of a rational function under the following conditions. The value a causes the denominator to be 0, but there is a reduced form of the function's equation in which a does not cause the denominator to be 0. So this is an example of what we're talking about up here in C. So our domain says that x cannot equal -3 and 3. We know we have a vertical asymptote at x equals 3. So then what's happening at x equals -3? And the answer to that question is there is a hole. At x equals -3. So on your homework, it's going to ask you, it's going to give you like multiple choice options of which you can choose on. There are no vertical asymptotes, there are no vertical asymptotes but a hole, there is vertical asymptotes and a hole. So make sure you read all the different options, but this example is going to help you the most. Okay, so talking about holes, let's talk about what that looks like on a graph, because unfortunately when we look at our graphing calculator, unless you zoom in on where that hole is, you're not actually going to see it. So we have this example, f of x equals x squared minus 4 divided by x minus 2. We know for our domain, x cannot equal 2. If we factor our function, f of x, it equals the quantity of x plus 2 times x minus 2 over x minus 2. Our binomials of x minus 2 will cancel in the numerator and denominator, leaving us the function f of x equals x plus 2. Okay. So that graph is a line with a y-intercept of 2 and a slope of 1. And we know, because we had that cancellation, we have no vertical asymptotes, but we have a hole at x equals 2. Now, when we're graphing by hand, it's helpful if we can be more specific with that hole. So to find the hole, we're going to plug that back in. So we have f of 2, and we're going to plug that into our simplified expression. So 2 plus 2, which is 4. So our hole is going to be at the ordered pair 2, 4. All right, so if we graph this, we have a hole at 2, 4. We have a y-intercept of 2. And we have a slope of 1. And then we're going to draw our line, straight line, leaving that hole or that open circle where it's at. And that is the graph of the function. All right. The next part of a rational function is our horizontal asymptotes, which are going to be dashed lines that are horizontal. Okay. We use the line y equals b as a horizontal asymptote of the graph of the function f if f of x approaches b as x increases or decreases without bound. Unlike vertical asymptotes, a rational function can have at most one horizontal asymptote. Also, although a graph can never intersect a vertical asymptote, it may cross its horizontal asymptote. This happens very rarely, but it is possible. So when we look at horizontal asymptotes, we have 3 rules, and they're all determined based off the degree of the numerator and the degree of the denominator. Now your book uses n and m. I think it's easier if we change this denominator to d. So I'm going to change all of these m's to d's, because I think it just makes it easier to remember the 3 cases. So our first one says that if the degree of the numerator is less than the degree of the denominator, the x-axis, or y equals 0, is the horizontal asymptote. If the degree of the numerator equals the degree of the denominator, then the line y equals a sub n over b sub m is the horizontal asymptote of the graph. All this is talking about is we're looking at the leading coefficients. Looking at the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, the graph has no horizontal asymptote. It has an asymptote called a slant or oblique asymptote. And for time's sake, we're going to skip over that. All right, so if we want to find our horizontal asymptotes, looking at A, f of x equals 4x divided by 2x squared plus 1. So because we don't have an exponent here, I'm going to put a 1. So the degree of our numerator is 1. The degree of our denominator is 2. And since 1 is less than 2, our horizontal asymptote is going to be y equals 0. And just like when we looked at our vertical asymptotes, we have to make sure we include that y equals. Okay, b, g of x equals 4x squared divided by 2x squared plus 1. So the degree of our numerator is 2. The degree of our denominator is also 2. Since 2 equals 2, our horizontal asymptote is going to be based off of our coefficients. So our leading coefficient of our numerator is 4. And the leading coefficient of our denominator is 2. And if we were to simplify 4 over 2, we get the line y equals 2. And C, h of x equals 4x cubed divided by 2x squared plus 1. So the degree of our numerator is 3. The degree of our denominator is 2. And since 3 is greater than 2, we have no horizontal asymptotes. All right, now we're going to combine all of that together and add a few more things in. So when we're graphing rational functions, we're going to go through these 7 steps. Some of them we're going to be a little bit more detailed on than what we have in the past. So first thing we're going to look at is determine whether the graph of f has symmetry. So we're going to plug in f of negative x and simplify and see if we get back the original or get back the opposite. Then we're going to find the y-intercept by plugging in 0. The x-intercept by finding p of x equals 0. And I'm going to abbreviate this. We're going to actually say this is the numerator equal to 0. Our vertical asymptotes we already talked about, but just to make it a little easier, it's our denominator equal to 0. But also don't forget to make sure that we're simplified and we look for holes. Horizontal asymptote, we're using our 3 rules that we just talked about. Now, the one thing that your book is going to have you do, that I'll show you a shortcut, is it's going to have you plot at least 1 point between and beyond each x-intercept and vertical asymptote. This we're going to use the table on your graphing calculator. And then we're going to connect all those points and make our graph. All right, so if we look at this first one, f of x equals 2x minus 1 over x minus 1. So first thing we're looking for is symmetry. So for our symmetry, we're going to plug in f of negative x. So we have 2 times negative x minus 1 over negative x minus 1. 2 times negative x is negative 2x minus 1 over negative x minus 1. So if we look at what we just got back with our original, we're checking to see did all of our signs go back to the way they were, and that answer is no. And did all of our signs change? And that answer is also no. So we have no symmetry. Okay. Second thing we want to find is our y-intercept, which means we're going to plug in 0. So we have 2 times 0 minus 1 over 0 minus 1. Nice thing is when we bring 0 in, we can just ignore everything other than our constants. So we have negative 1 over negative 1, which equals 1. I'm going to go ahead and plot that point on our graph. Okay, third, we have our x-intercept. So we're going to set our numerator, 2x minus 1 equal to 0. If we solve this, we have 2x equals 1, x equals a half. One thing that I like to do with the x-intercepts is also look at the multiplicity. So here our multiplicity is going to be 1 because there are no exponents, which means we cross through. Go ahead and plot that point on our graph. All right, now we're going to bring in our vertical asymptotes. Okay, because our original function is already factored and simplified, we can just look at our denominator. So x minus 1 equals 0. Tells us that x equals 1. And we're going to graph that with a dashed vertical line through our x-axis at 1. Fifth, we're going to find our horizontal asymptote. So the degree of our numerator is 1, and the degree of our denominator is also 1. So these are equal, which means that we look at our leading coefficients. So y equals 2 over 1, or just y equals 2. So I'm going to go up to 2 on our y-axis, and I'm going to make a dashed horizontal line. Okay, so now we have a couple different ways we can graph. So if you're graphing by hand, the key thing to know is that majority of the time you cannot cross a horizontal line that's dashed, and you can never cross a vertical line that's dashed. So if we're looking at whether or not we're going to graph up here at the top or down here at the bottom, we know we're going to be graphing here because we have these 2 points. Okay. But what you're going to do in your homework is it's going to actually give you a table. So for your homework, you're going to be given a table that's going to ask you to fill in, where it's going to give you some x values. So let's say it gives -2, 1/4, 3/4. Let's go 2 and 7. Okay. Now, if you were to do this by hand, you'd be taking each of these x values, plugging them into this function, and simplifying, which is perfectly fine. But you also have your graphing calculator that you can use as a resource. So I'm going to kind of jump over to this app, Calculate 84. It's not going to work as well as your graphing calculator will, but it'll at least be able to show you the process. So we're going to go to our y equals. Oops. We're going to type it in to our y equals, but make sure you're using the fraction button on your calculator. If you are not used to using the fraction button on your calculator, remember it is the green button, alpha, and the button to the right of it, x. If you have one of the older calculators, you're going to want to hit alpha, y equals, and then hit enter. Either of those will work. If you need to borrow one of my calculators, just make sure you borrow one of my calculators. Okay, once we have that plugged in, we want to go make sure that our second window and our independent is back to ask, like what we were doing in our previous unit. And now we can go to our second table and we can type in our values. Now, if you're using one of the graphing calculators, it'll actually spit out your answers as fractions, which is what your homework wants you to put it in as. Unfortunately, the app puts everything in as decimals. So, jump back to the notes, and I just wanted you to see that you could fill that in. Okay. Also, you can look at the graph on your calculator and see the shape of our graph. So if we finish this off and graph it, we're not crossing any of our asymptotes in this graph. So we're going to get really close to it. We're crossing through that x-intercept, similar to that multiplicity we talked about previously. And then we're going to jump back up to the top. When you get to the bottom of an asymptote, you usually will jump to the top of it. If you get to the top of an asymptote, you jump back down to the bottom. And then this is our graph. Okay. We're going to state our domain and range. So our domain, our only x value that's not included, is 1. So the domain is from -infinity to 1, union 1 to infinity. And our range, if I can spell range, it's helpful, is going to start from -infinity, and then our horizontal asymptote is 2, union 2 to infinity. And we're using parentheses because we're not actually touching that y value of 2. All right, last example. F of x equals 3x squared over x squared minus 4. So, starting off, we have our symmetry. So we're going to plug in f of -x. So we have 3 times -x squared over -x squared minus 4. -x times -x is a positive. So we have 3x squared over x squared minus 4, which gives us the same thing as what we started with. So this means we're symmetric across the y-axis. Okay, second, we're going to find our y-intercept. So we're going to plug in 0. We get 3 times 0 squared over 0 squared minus 4, which simplifies to just be 0. I'm going to go ahead and plot that point. Third, we have our x-intercept. So we're going to take our numerator and we're going to set it equal to 0. So we have x squared equals 0, which tells us that x equals 0 with a multiplicity of 2, which tells us when we graph, we're going to bounce back. All right, now we're going to talk about our vertical and horizontal asymptotes. So starting with vertical, we need to factor and simplify our fractions. So we have 3x squared. Our denominator can factor to be x plus 2 and x minus 2. So nothing cancels. Which tells us we have no holes. And then looking at our denominator, our vertical asymptotes are going to be x equals -2 and x equals 2. I'm going to go up on our graph and draw those dashed lines. Notice they are symmetric across the y-axis, which matches that very first step that we did. Okay, lastly, before we graph, our horizontal asymptote. The degree of our numerator is 2, and the degree of our denominator is also 2. Since those are equal, we're looking at our leading coefficients. So we have y equals 3 over 1, or just y equals 3. Okay, zooming in on this graph. Again, you can use your graphing calculator to help you get the shape, but let's talk about a couple of things. So this is the only point on our graph, and we can't cross any of our dashed lines. So our graph cannot go up top. It's going to have to go underneath. And we also know that at that x-intercept, it's bouncing back, so it's like a parabola. Okay. Then we need to talk about what's happening on the left and the right. We know they're symmetric, so whatever we're doing over here, we're going to do the same thing over here. But notice there aren't any x-intercepts to the left of -2. So we can't cross this x-axis, which means it forces our graph to go up here to the top. This is another reason why we fill out the table to help us find our x values when we don't know where we're going. But if you have your graphing calculator, I'm perfectly fine with you just plugging it into the y equals and looking at the shape of your graph. Okay. All right, just like how we finished the last one, let's find our domain and range. So our domain here, we had 2 vertical asymptotes. So we have -infinity to -2, union -2 to 2, union 2 to infinity. And then our range, we're starting down here at the bottom at -infinity, and our graph is going up and stopping at 0. Now, because we have a point at 0, instead of using a parenthesis, we're going to use a bracket. So we have -infinity to 0 with a bracket, union. Now our graph jumps. We have nothing happening from 0 until 3. And at 3, we're getting really close to the line, but not actually touching it. So we're going to use a parenthesis, 3 to infinity, because our graph is going to keep going up as it gets closer to x equals 2 and -2.